So the problem here is to solve a 3y double prime of x plus y prime of x minus 2y of x equals 2 cosine x with the method of undetermined coefficients and variation of parameters. Now this one is a little weird because here they ask you to solve with variation of parameters, even though using undetermined coefficients is much easier. So this is basically just a proof of concept. So I guess the idea of motivating this problem is just that you want to verify that the variation of parameters method works for the specific problem, because the variation of parameters is a more general way of evaluating or solving differential equations, or like non-homogenous differential equations. So here we go. So undetermined coefficients is much easier because you just have to, you know that the set or the solution is just y equals yc plus yp, where yc is the set of solutions that works for the complementary equation, and yp is the ones that work for the other case. Let me check what that's called real quick. That's a I forgot. Oh, a particular solution. That's what it's called. Yeah. So yeah. Now let's just get started. So basically what you do here is finding the complementary equation is just a 3y prime of x plus y prime of x 2y of x equals 0. And the auxiliary equation of this is a 3r squared plus r minus 2, and we know that when solving for the roots, that gives us the coefficients of e, because the solution will ultimately come in the form, for the complementary equation, the solutions will come in the form c1e to the, I guess, r1x plus c2e to the r2x. So this is what we're expecting, and factoring this out, we just get 3, let's see, plus and then plus 2, so it's positive. So yeah, I think this is it. So this implies that the roots are, well, what solves this is 2/3, so it's 2/3, and what solves this is -1, so the roots are 2/3 and -1. So we can say that yc equals c1 e to the 2/3 x plus c2 e to the -x, right? So that's definitely the easiest part of doing this. Now, what differs between solving with indeterminate coefficients of variation of parameters is how you solve for the particular, or the y sub p part, basically. And that basically differs a little bit. It's definitely easier if you're doing variation of parameters, or sorry, undetermined coefficients. So basically, what you do here is you just take a, you basically want to find, let's see, let me think about this real quickly. So it's kind of like solving for a system of equations, whereas you have to do a bit more, so to say, legwork with a method of variation parameters. So basically what you do here is you basically think of a form for what this will come in. So basically, you can say that y sub p, it has to come in some form that will spit out 2 cosine x. So assuming that you can achieve that with some kind of like combination of sines and cosines, you can just say a sine x plus b cosine. Or actually, no, it's more efficient. It's more appropriate to do a cosine x plus b sine x, just because the order is a bit nicer that way. So if we say this is y sub p, then we can also determine that yp prime, just prime, is a sine x plus b cosine x, and then y double prime p is a cosine x minus b sine x. Okay, cool. So now that we know all of this, we can basically substitute in these for the y prime x, y double prime x, y prime x, and y of x into this equation, right? So what we get here is 3y double prime x, so that's 3a cosine x minus b sine x plus y prime, so that's just a minus a sine, and then minus 2yx, just keep it consistent, and then minus 2b. Okay, and then now you just basically group like terms. So here's a 3a. Here's a b. And here's 2b, or negative 2b. And then now grouping signs. Negative a. Let's see, did I mess that up? Oh, hold on, that's a 3b. My bad. Then minus a 2a, 2b. And then now we can basically state that we can make some equations. So because this right side is only in terms of cosines, the sides add to 0, and then the coefficients of the cosines must add to 2. So thus we can make a system of equations. 3a minus 2a, yeah, I messed that up, my bad. So it's 5a plus b equals 2. And then here we have a negative 5b minus a equals 0. So these are sines, cosines, and now we can just basically solve. So 5b, so that's fine. And then just plugging in that for a here, you just get a 25. Let's see, hold on. Yeah, 25a plus, oh wait, sorry, 25b equals 2, so equals just 113. Yeah, and then subbing that in here, because b is 1/13, a must be negative 5/13. So then now what we can do is just substitute back into the form of the particular equation. It must be in the form a cosine x plus b cosine x. So we have the whole solution y equals yc, the complementary equation. C1 e to the 2/3 x plus C2 e to the x, and then adding the particular negative 5/13 cosine x, and then plus 1/13 sine x. So that's the undetermined coefficients. Now solving with the variation of parameters, you solve for yp differently. So yc is basically the same. So basically what you do here is you the reason why they call it variation of parameters is that you substitute in functions u1x and u2x for c1 and c2 respectively, and basically to work that way. So you have u1x y1x plus u2x y2x. So now what you want to do here is I guess you could go back and drive the solve, but it's not really necessary. What it boils down to when you're working with this method is that you end up with these two equations, u1 prime x y1 x plus u2x, y2x equals 0, and then the other one is a u1x, y1 prime x plus u2 prime x, y2 prime x equals g, which is basically the solution. So, or I mean, g is basically what you get when, g is this value 2 cosine x here in terms of the polynomial. So like usually when you work with like non-homogeneous differential equations, it just, like at least the second order how it's written, it's like ax squared plus bx plus c equals g of x, and that's what's going on here. So it'll be 2 cosine x in this case. So you have these two equations, and basically you can do the heavy lifting to do this, but basically what it boils down to is finding out what u1 and u2 are. So u1 prime we have defined as g y2, yeah, a y1 y2 prime minus y2 y1 prime, u2 equals gy1 a y1 y2 y2 y1. Okay, so we have all this information, and we also have y1 and y2 are, of course, e2 to the third, or 2/3 x, and then y2 is e to the negative x, right? So we have this, and now we can solve for this bottom part since that's useful. Also, looking at this, the coefficient a here is 3 for the specific differential equation we're working with. A is 3, and g is 2 cosine x. So that's useful information. So now we can find this value. So y1, 2/3 x, y2, negative x, and then y2, y1, taking the derivative here, that gives, you're adding, so you're subtracting both, so it's just adding like 1 plus 2/3, so you get a 5/3, negative 5/3, and you multiplying these exponents is like adding the powers, so it's 1/3 x here. So that's a y1, y2, that's y2, y1, so y2 prime, y1 prime. So that's what you get here. And then a, of course, 3. So the bottom part is just 5 e to the 1/3 x, which is really useful. So now we can solve for u1, which is just a and then gy2, well, y2 is negative x, 2 cosine x. And then you can simplify this a little more, and that just becomes that's just equivalent to saying e to the 1/3 x over e to the x, which is then 2 over 5 cosine x e to the negative 2/3 x, and then u2 is oh yeah, also that's an important detail. This is a negative, so now multiplying the two negatives, this just becomes positive. Important detail. And then u2, there's no negative sign here, so it just becomes a 5e 1/3 x, and gy1 is 2 cosine x of e 2/3 x. So this is kind of like just multiplying it up, so it just becomes a 2/5 cosine x e to the x, right? So that's kind of nice. So now basically we want to find what is u1 and u2. So here we can deal with this a bit easier. So like now notice this is a product of functions, so we can determine u2 by integrating using the using integration by parts. So now I just want to do 2/5 cosine x e to the x is just so we're not going to include the constant here. But yeah, we want to choose a good u and v respectively. So what we would do here is, let's see. Well, exponents are a bad choice for the u spot, so we would choose a cosine x for u, and then dv would be e to the x dx, super convenient. So now we can just say this is equal to uv, so uv would be ex cosine x minus v du, so v would just be e to the x, du would be negative sine to the x. Okay. And then we can just perform integration by parts again with this part, saying u equals sine x, dv equals e to the x dx, so that's just equal to e to the x cosine x plus uv, which would be sine x e to the x sine x, and then the integral would be a minus v du, so that's cosine x v du, oh, whoops, that's du, and v is of course e to the x, so that's ex cosine x. And what you can do now here is basically solve. So basically what you're solving for in the first place is this value, 2/5 cosine x e to the x dx. So you're solving for that first, and let's see. Okay. Because these integrands are the same. So I might transfer to a different piece of paper, because the next one is going to be even more complicated. Okay, so let's see. Okay, so cosine x e to the x dx equals cosine okay, so now we want to make this 2/5. So we really want 2/5. So now multiplying this by, let's see, 2/3. Yeah, I think 2/3. Unless I'm doing something wrong. Yeah, because, let me think about it. Yeah, it's just because I'm kind of rusty, so 3/5, yeah. That doesn't make that much sense though, because I've gotten something different for what I inputted on the calculator. So there may be some sort of a computational mistake I made, or some sort of mistake I made when integrating. Ooh, yeah, that's the mistake I made. I just completely forgot to put this in at all. So I have to, of course, slap this in somewhere. So that's just yeah, cross that out. So 2/5, I guess we can say, we can assign 2/5 here, 2/5. So it's just the whole thing is times 2/5. And then now this Let's see. When I think about it, because there's something up here. Yeah, because v and dv would both have this component. So now these v and dv would still have the same component here, because you'd have a 2/5 in here, right? So plus 2/5. But that doesn't make sense. Let me think about it. Let's see. Yeah, this is a little complicated, so I just want to make sure I'm doing things correctly. Yeah, it's kind of a crazy integral. Okay. I mean, we can just multiply 2/5 at the end. I think so. We can just keep that here, and then just solve a cosine x e to the x, really. And then we're basically just doing that, right? So okay. Well, cosine x e to the x, based on what we did earlier, is e to the x cosine x plus e to the x sine x. And then now we've got a dx. So adding that over, we've got a 2 plus e to the x cosine x. Sorry, that was I messed that up a little bit. So now we have 2 cosine x e to the x dx equals. So we can divide 2 over, e to the x sine x plus e to the x cosine x over 2. And now multiplying by 2/5. Just get a negative u2 e to the plus cosine x equals this, basically. So yeah, that's u2, which is actually simpler than u1. So now u1, I'm going to work with this one. Same procedure, really. So you're doing the same thing where you solve for the left side of the equation for the integration by parts. So 2/5 cosine x e to the So we can just solve for this part first. So it's just cosine x to the e to the negative 2/3 x. We just want to do the integration by parts. So uv, so cosine x times 3/2. Okay, so that's uv, and then minus v du. So This is u, du is just sine x, so it's plus this dx. And then performing it a second time, 3/2 cosine x e to the 2/3 x plus, let's see, u is sine x plus sine x times negative. So, continuing with the problem. Let's see. So where am I? So I'm completing the integration by parts on this integral, right? So it's just a u dv or uv. So u would be this term, and then v would be negative 3/2 e to the 2/3 x, and then minus v du. So I designated this as v, so it's e to the 2/3 x. Du would be a cosine x dx, and then now we've just got a cosine x e to the 2/3 x dx, and we've got the same integrand, so now we can basically pull that over and deal with this basically. I don't think there should be anything wrong here either, but it's always good to make sure. So got a 3/2, 3/2. Hold on, let me think about this, because uv, let's see, I just want to make sure as well. Hold on for a second. Yeah, that is a bit weird. Let me think about it. Yeah, there is something kind of weird going on here, so. Okay, so this is, that's fine. And then, yeah, so this is uv. So this is our u, and this is our v. And then this is a v. Oh, yeah, there we go. Times 3/2. That's what we're missing. So that's why this isn't quite right. So now I gotta go through this process over again. So 3/2 cosine x e to the negative 2/3 x, and then this is just 3/2. And then now we can evaluate this integral as well. So that's a 3/2. Let's see. So yeah, that's the only weird thing, I think. Yeah. So you've got 3/2 already there, and then now you've got let's see. So you've got a sine x times negative 3/2 to the negative 2/3 x, and then minus 3/2 e to the negative 2/3 cosine x dx. Okay, so we've got that going on, and then this is just equal to that as well. So, man, this is really cumbersome. So now we can basically just multiply this out. So we've got a 3/2 cosine x e to the negative 2/3 x minus 3/2 well, plus 9/4 sine x e to the 2/3 x plus 9/4 2/3 cosine x dx, and then adding that to the other side, we've just got a, let's see, so that's 4/4, and then this is 9/4, so we're, is there a sign I'm missing somewhere? Plus, oh, that's, so this, you're just subtracting twice, so this should be adding, and then you're multiplying by a negative, so it should be subtracting. So you're adding it to the other side, so it's just a 13/4 cosine x e to the 2/3 x dx equals this stuff over here. So 3/2 cosine x to the 2/3 x plus 9/4 sine x e to the 2/3 x. Okay, so now we've just got a, basically we can isolate that, and I might carry this over to this part of the page. So it's times 4/13, and really this is just a 2/5, so we multiply 2/5 on both sides. And then now we've got a 8/65. All of this. And for ease of calculation, let's just bring out this portion, right? So now we've got a u1 equals, well, we can do some stuff here as well. So let's see how we can simplify this a bit, because it is a bit messy currently. Well, we can multiply in the 8 to clean some stuff up, right? So now we can just say 1/65, so we multiply for 8 both times. So 3/2 times 8, that's just 3 times 4, which is 12 cosine x. And then we're multiplying by 8 here, so 9/4. So that's really just 9 times 2, which is 18 sine x. Times e to the negative 2/3 x, right? So that's our second, or that's our u1, and we've got a u2 over here. So this is all we need out. So remember at the beginning of the process I said the particular solution looks like this: u1 y1 plus u2 y2. So we know that y1 equals e to the 2/3 x, which will cancel out this, that's why I isolated that. And then y2 equals e to the negative 2x, so we can cancel that out from here. I forgot to factor it out, but we'll see what happens here. So basically what we end up with is 18 sine x minus 12 cosine x over 65 plus multiplying 13 on the top and bottom to establish a common denominator. 13 sine x minus 13 cosine x equals 65. And when we add these two together and simplify, we just get 18 minus 13, which is 5 sine x over 65, which is just sine x over 13. And let's see if this is what we have here. So sine x over 13, and then we have for a cosine, we've got 25 over 65, which is 5/13. So that's minus 5/13 cosine x. And this is actually the same exact thing we get for the particular solution in this part, hence why there's no reason to really do the variation of parameters for this particular type of problem. So yeah, that's how you do it. So that implies that the solution here is once again c1 e to the 2/3 x plus c2 e negative x minus 5/13 cosine x plus 1/3 sine x.